In this video, we'll introduce some basic definitions and equations that we'll be using throughout our semester discussion on thermodynamics. We'll start with the universe. Of course, you can't get much bigger than that, but in thermodynamics it has a specific definition. Particularly, we define the universe as being composed of the system and the surroundings. Now, the system is what we are studying, such as a gas enclosed in a container of some kind. And the surroundings would be everything else, everything outside of the system. Beyond that, we'll have two basic terms that we use to describe the thermal conditions within our thermodynamic system. Diathermal refers to a situation in which heat transfer is allowed. For example, we have two containers in contact that allows heat to be transferred through the walls of those containers. Those walls are said to be diathermal. Adiabatic refers to a situation when no heat transfer is allowed at all, and this would be something where we have a system in an insulated container and we do not see any heat transfer with the surroundings at all. We have a situation corresponding to thermal equilibrium when we have two systems which are have the same pressure, temperature, and concentration. They are in thermal contact, and that would be a situation where they might be in contact through walls that are diathermal. Now, we will also have different types of variables in our thermodynamic system. One specific type is a variable that's referred to as being intensive, which means that it does not depend on quantity. Variables of this type would include pressure, temperature. Temperature obviously doesn't depend on the amount of stuff that you have. And then we have extensive variables, which do depend on the amount. Volume obviously is an extensive variable. Composition, mass, things of that nature are extensive variables because they do depend on the amount of stuff that we have. And then, of course, we move on to the ideal gas law. We'll, of course, be talking about other types of systems throughout our semester, but we have to start with the simplest system, and that's the ideal gas. Everybody should remember from general chemistry that the ideal gas law corresponds to PV equals nRT, where P is equal to pressure, V is volume, N is the number of moles, R is the gas constant. The value of the gas constant will depend on the units that we use. For example, if we're using units of liters for volume, atmosphere for pressure, Kelvin for temperature, and moles, of course, for moles, that the value is given by this number here, 0.08206. However, the gas constant can also be represented by 8.314 joules per Kelvin per mole, and we'll find that useful under certain circumstances. The thing that's important to note about the ideal gas law is that it depends on the amount of stuff and not the identity. It doesn't matter whether our gas is helium or argon or oxygen or nitrogen, whether it's atomic, monatomic, or diatomic or polyatomic. The ideal gas law is the same. Now, because of this, there are some basic assumptions that are built into the gas law, because as you can imagine, there will be times when the identity of the gas is important, and we'll be talking about that later in the semester. The important assumptions to note are that there are negligible interactions between the particles, no attraction, no repulsion between our particles, and that they're infinitesimal in size, that they have essentially zero size. And the reason for that is that with negligible interactions and negligible size, then clearly the nature of the particular gas does not matter. Now, we'll find that the ideal gas law, which was empirically determined, works best under conditions of low pressure, because when the pressure is low, the spacing between the particles is large enough that the size is not important, and there's very little interaction between the particles when they're spaced far apart. And also at high temperatures, when at high temperatures the particles are moving about at such high speeds that their interactions also are negligible. Now, it just so happens that when the ideal gas law was first determined, the scientists who were responsible for collecting the empirical data and analyzing it to come out with the gas law were working at these conditions for the particular gas. And for gases at room temperature, like helium, for example, we'll find that room temperature and room pressure and 1 atmosphere pressure really is such that the ideal gas law works very, very well. Now on this page we see something that's referred to as an isotherm. Isotherms are constant temperature plots where under conditions of constant temperature we'll note that the pressure and volume are inversely proportional. If we have a plot here, we have the pressure along the vertical axis and the volume along the horizontal axis. Each of these curves corresponds to different temperatures. So we have this curve here corresponding to 700 K on top, and at the bottom of this set of curves we have 200 Kelvin, a much lower temperature, and of course 600 would be the next one there. What's important to note here, of course, is because pressure and volume are inversely proportional, that as the volume goes up, as we move from left to right here across our graph, the pressure will go down. This is something, of course, that you should remember from general chemistry. Now, because the gas law is independent of identity, depends only on the amount, you can imagine that a mixture of gases will also behave as an ideal gas because it only depends on the number of moles of gases, the total number of moles. And from this we get Dalton's law, also something that you discussed in general chemistry. Here we see Dalton's law, where this top equation here shows that the total pressure is the sum of the pressures of the individual gases, which are called partial pressures. So for example, if we have a mixture of helium and nitrogen, the total pressure is equal to the partial pressure of helium plus the partial pressure of nitrogen. And that these individual gases also behave as an ideal gas, so that the partial pressure of any given gas depends on the number of moles of that gas and the total temperature. And the volume in this equation would be the total volume of our container. Okay. Now, we also have a situation where the partial pressure may be related to the total pressure through the mole fraction, where the mole fraction is very simply just equal to the number of moles of a given gas divided by the total number of moles of gases present. And finally, of course, the overall pressure, the total pressure of our mixture also behaves as an ideal gas and follows the ideal gas law, where the number of moles in the equation is the total number of moles of all the gases combined. This ends our first video detailing some basics and just a review of some basic equations in thermodynamics. In our next video, we'll look at the behavior of gases in a little bit more detail and actually discuss some of the issues associated with a real gas that behaves according to different characteristics.